Let's talk about the critical path method. The critical path method is one of two ways that you can, or one of two tools that you can use to identify the paths through your project. The other way is called PERT, Program Evaluation and Review Technique. The difference between critical path and PERT is that critical path uses one time estimate, whereas PERT uses 3 time estimates. So critical path is more or less for when you're pretty sure about the durations, the time it's going to take to do each task or each activity, whereas PERT is used in a more uncertain situation. You remember our discussion about uncertainty? And you can use these 3 time estimates to come up with something called the expected time. We're going to start with the critical path method since it is the simplest way. We're going to use a method that's a little different than in your book. We're going to use this key. This key, if you'll notice in the center block, that is that A represents activity, and down here D represents duration, whereas ES is early start, EF is early finish, LS late start, and LF late finish. Over here we're going to have S, which is equal to slack time. You'll notice this block right here where I have the diagonal lines. All that is a block where you can write a description in of the activity if you choose to do so. So let's get into the details of critical path. When you're using the critical path method, you need 3 pieces of information: activity, predecessor, and duration. You need to have the activities listed. You need to know which activities are predecessors to other activities, and then you need to know the time that each duration will take. In this instance, we're going to use weeks as our unit of time. So using this information, we can draw a precedence diagram. And if you look at the precedence diagram, you can see all of the paths that go through our project. And there are many different paths. This means that some activities can be done concurrently, simultaneously. Some activities, though, cannot be done that way. They have to have the previous activity completed before you can move on. And so this drawing, this precedence diagram, gives you a pictorial view of what the project should look like. We can use this diagram to go through and identify our tasks, or I'm sorry, our paths. For instance, we have paths A, C, F, and I. We have path A, D, H, and J, path A, D, G, and J, and path A, E, H, and J, B, F, and I. So we have 5 paths through this project. We can go through and we can use the information that we had for each one of these activities, and we can identify what the critical path is. So what is the critical path by definition? Well, if you'll remember in class, we talked about the critical path as being that path that if you had any delays on, it would delay the entire project. That means that there is 0 slack time associated with the critical path. Right now, all the information we want to know is which one is the critical path. So we can go through and we can add up each one of the activity times, and we can see that for our first path it's 18 weeks, second 19, third 18, fourth 21, and fifth is 14. So what does that mean to us? Well, what that means is that our critical path is A, E, H, J, because it takes 21 weeks. That's the longest duration of any path in our project. And what that means is that these activities are not going to have any slack time on them. And that is the path that we're going to monitor through our project. So we're going to use this and use my boxes now. And I've drawn out the network, and this is what it would look like with the boxes. So the first thing that we're going to do is we're going to do something called a backwards pass. Excuse me, we're going to do a forward pass. Okay? That means that we're going to move from left to right. In case y'all don't remember when you were in class, I told you I was dyslexic. Remember that. All right. So we're going to start with activity A. And if you remember, a starting activity begins at time 0. So our early start for activity A is going to be 0. The same thing for activity B, because if you remember on our information, activity B had no predecessors. Okay, so now we want to calculate what the early finish time is going to be. To calculate early finish, we're going to take early start and add the duration. So 0 plus 5. 0 plus 4. All right, so we've done the first 2 tasks. Now we're looking at this diagram and we see out of activity A that we have 3 arrows. We don't have to make any choice. We automatically know that the early start for each one of those activities is going to be 5. Again, we're going to calculate the early finish. 5 plus 3 is 8, 5 plus 4 is 9, 5 plus 6 is 11. Well, now we get into a little bit of a dilemma because we see all of these arrows going all different directions, so we sort it out. Okay, for activity F, right here, we have 2 activities that feed into it, C and B. We have to make a choice. You see that we have an early finish of 8 for activity C and an early finish of 4 for activity B. Remember by definition that the path, all of the activities have to be complete, all of the predecessor activities have to be complete before the new activity can begin. That means that we have to choose the highest of the 2. So we're going to choose 8 for our early start for activity F. For activity G, we only have one predecessor, which is D, so we don't have to make any choice. So for activity G, we're going to have 9 as our early start. For activity H, we have activity D and activity E that feed into H. So we have to look at those early finish times and we have to determine which one is going to be our early start for activity H. Activity D has a early finish of 9 and activity E has an early finish of 11. We're going to choose the higher of the 2, which is going to be 11. 11 plus 6 is 17, 9 plus 5 is 14, and 8 plus 4 is 12. So now we need to come over here to activity I. Activity I, we have no choice. We know our early start is 12. 12 plus 6 is 18. For activity J, we have to choose between the early finish for activity G and activity H. H has the larger number, so we're going to select the larger number for our early start for J. So 17 plus 4 is 21. If you'll remember, when we looked at our each path individually, the path that we selected had a duration of 21 weeks for the critical path. Well, that doesn't really give us a whole lot of information. We still don't have any more information than what we had when we just went through it and identified all the paths and added up the slack time. So what we want to do now is something called a backwards pass. When we're beginning our backwards pass, we're going to start with the late finish. Now, in order to calculate our late start, we're going to take our late finish and subtract our duration. But we have to get started on this. We have 2 ending activities. And I know when you were on class, you probably never saw this because all of the ones that we did had just 1 ending activity. When you have 2 ending activities, you have to select between the 2 times. So for activity J, which is an ending activity, it's 21 weeks, and for activity I, it is 18 weeks. Well, for both of these activities, we're going to use 21 to start our backwards pass, because remember, 21 weeks equals the duration of the project. Everything has to be completed in 21 weeks. So now what we're going to do is we're going to calculate the late start for activity J. 21 minus 4 is 17. For I, 21 minus 6 is 15. So we're going to take 17 and we're going to transfer that into activity H and G as the late finish. And we're going to transfer 15 for activity F as the late finish. 17 minus 6 is 11. 17 minus 5 is 12. 15 minus 4 is 11. So now we've got to be a little bit careful because we're back in that situation where we have multiple arrows coming in and out of activities. So let's start with activity E. Activity E, we have one arrow. Okay, you see where it comes backwards here? So we're going to take 11 and transfer it down here. We don't have to make a decision. We know it's going to be 11. 11 minus 6 is 5. For activity D, well, now we've got to make a decision because we have two arrows coming backwards. Now remember, this is a backwards pass. That means that our rules have now reversed. So at this point, we're going to look at those late start times and we're going to choose the lowest of the two. So in this case, we're going to choose 11. 11 minus 4 is 7. So for activity C, we have one activity, which is F. You see the arrow right here. So we're going to transfer 11 up here for the late finish. 11 minus 3 is 8. Okay, so for activity B, we don't have to make a decision because the only arrow that we have is the arrow leading to activity F. So we know that that is going to be 11. 11 minus 4 is 7. For activity A, however, we have to make a decision. We see that we have activities C, D, and E that come after activity A. So we need to choose the lowest of the late start times for our late start for activity A, and that happens to be 5. 5 minus 5 is 0. We still don't have a lot of information. We can look at this and we probably could off the top of our heads identify the critical path because we know by definition that it's going to be the activities that have 0 slack. But now that's what this little box is for right here, is to calculate slack. And to calculate slack, we can do it one of two ways. We can calculate slack looking at the late finish minus the early finish, or we can look at the late start minus the early start. Either formula you use, you should come up with the same answer. This is a really good checkpoint for you because you know that if you've got something off where you don't come up with the same slack time using either of these formulas, then you've done something wrong in your diagram. So let's go through and calculate slack time. For activity A, we're going to use late start minus early start, so 0 minus 0, that's going to be 0. Now let's check out here. 5 minus 5 is 0 as well, so we know we're correct. For activity B, 7 minus 0 is going to be 7. And we can check here, 11 minus 4 is 7. We're going to go through and calculate the slack for each one of these activities. Now we can easily identify the critical path, and now we know which activities have slack time and which activities don't. If you'll think back, when we identified the critical path previously, we said that it was A, E, H, and J. If you look at A, E, H, and J, you see that each one of those activities have 0 slack time. Okay? The rest of them all have slack. What does slack mean? Well, that means that for activity B, we can actually wait 7 weeks before we start that activity. So we've got some leeway in there. What if we had valuable resources allocated to activity B? Well, now for 7 weeks we can free up those resources. We can use them in other parts of this project, or we could use them on another project. So this gives us a way to analyze our project and start trying to figure out how we can allocate those resources. And it also helps us in the budgeting process that we've talked about previously. So that's the critical path method. As we started out talking, I told you there was a second method. It's called PERT, Program Evaluation and Review Technique. PERT uses 3 time estimates. It uses a time estimate that is called A, that is the optimistic time. The optimistic time, that's when, you know how in life we think of people as having these sunny dispositions, everything goes right, there's never a down day, and we look at them like they're crazy. Well, that's what optimistic time is. You're thinking nothing in the world is going to go wrong, everything's going to go right, and this is the best time that we can complete that task in. Okay? Not really the way to look at it, but we're going to soften that some with our formula in just a few moments. The letter B represents the pessimistic time. Pessimistic time, that's when everything is going to go wrong. Nothing in the world goes right. This is the longest time that we can possibly think of that this task would take, given the fact that everything is going to go wrong. And then we have time M. In life we know that it's not always going to be the very best, and it's not always going to be the very worst. It's going to be somewhere in the middle, and that's what M represents. That's the most likely time. So we have those 3 time estimates that we have to deal with. And so when we look at how we're going to deal with those, we need to have some information, obviously. We have to know what the activities are and what the optimistic time is, the pessimistic time, and the most likely. Now you'll notice that this chart is laid out differently than I presented the time estimates, and that's because I've laid out the chart, and most books will lay out the chart the way that you're going to use the formula. Okay? So we have all of our time estimates here. So let's just calculate a couple of them real quick. Okay? We have our formula for expected time. You'll notice we have a column here, right here, for expected time. Well, our formula is A, optimistic time, plus 4 times the most likely time. Now, why would most likely time have a weight of 4? Well, that's because it is the most likely to occur. So we're going to weight that time more than the other 2 time estimates. You'll see that the pessimistic time only has a weight of 1, as does the optimistic time. So we're going to add all of those up, and then we're going to divide by 6. Why 6? Because we have 6 weights. Remember that we have an unseen 1 here and an unseen 1 here. So 1 plus 4 plus 1, 6. It's always going to be 6. That's constant. It will never change. So for our activity A, we can substitute in our time estimates. We have an optimistic time of 1 plus 4 times the most likely time, which was 2, plus the pessimistic time of 3. And we divide, that adds up to 12, and we divide that by 6, and we come up with 2. So now for our chart, we can come back here and we can simply fill in 2. Let's do one more. 2 is the optimistic time plus 4 times the most likely time of 3 for activity B, plus 4, which is the pessimistic time. That's going to add up to 18. We're going to divide that by 6, and so our expected time for activity B is 3. Everybody understand that? I'm sure you do. I know you don't want me to go through each and every one, so let's just fill in our chart. So now we have the expected time. We need some other information though. We want to know what the variance of each activity is going to be. We have a formula for the variance that we can use. The formula is the pessimistic time minus the optimistic time divided by 6, and then we're going to square that. So if we just do activities A and B, we can see that the pessimistic time of 3 minus the optimistic time of 1 divided by 6, so 2 divided by 6 squared, is going to equal 0.11. For activity B, the pessimistic time of 4 minus 2, so 2 divided by 6, square it, and we're going to again have 0.11. So we're just going to fill in our chart. Okay, so now we've got the expected time, we've got the variances of the activities, and so now we're going to make some basic assumptions about our project. We're going to assume that our critical path for this project is A, C, E, G, and H. What we want to know is we want to know what the project variance is. Well, I know y'all didn't think you were going to have stats again. Well, this is terrible, but you're going to have them. But it's not as bad as it was when you were in statistics. What we're going to do is we're going to calculate our project variance. Project variance is denoted as the following. And all it is the sum of the variances along the critical path. So we can go back to our chart now and we can figure out what that is. It's 0.11 plus 0.11 plus 1 plus 1.78 plus 0.11. That's going to give us a total of 3.11. So we know that our project variance is 3.11. We need another bit of information. We need to know what the standard deviation is. So in order to get the standard deviation, we're going to take the square root of the project variance. And that is going to be 1.76. Okay, so 1.76, Dr. Z, what does that mean? Well, what that means is that our project, the time, the duration of our project, is going to be plus or minus 1.76 weeks. Now that's a piece of valuable information, isn't it? We can do a lot with that information. We know that we could be in trouble. It depends on what this project is. In this case, this project is a compliance project. It is a project where the company has to put in an air filtration system. Otherwise, the EPA is going to shut them down. They have to do it within 16 weeks. So now that plus or minus 1.76 weeks becomes a whole different picture, doesn't it? Because if they are over by 1.76 weeks, they're going to shut their company down. They are not going to be able to do business. They're going to lose money until the project is complete. And then you've got to get people out there to inspect it. So it could be far longer than 1.76 weeks that they're going to be shut down. So we want to avoid that. Well, the first question out of your boss's mouth is going to be, what is the likelihood that we're going to be finished by this time? And most of the time, we give them a SWAG answer. I'm hoping everybody knows what SWAG stands for. Okay? So I'm not sure I should say it and let it be recorded. So look it up on the internet. And we're going to figure out what the probability of this happening is. You know, we have assumed this, and we're going to assume one other bit of information, and that is that the project duration is 15 weeks. Okay? So we have all of this information. So now we want to know what the probability of finishing this project is having it done by that 16th week. Well, we need something called a z-score. You remember those from statistics? Well, it's not as difficult either as it was in statistics. What we're going to do is we're going to use a very simple formula. Z is equal to due date minus expected date divided by the project standard deviation. So we said we had a due date of 16 weeks. Our project duration, we expect to have it done in 15 weeks. And we know that our project standard deviation is 1.76 weeks. So when we calculate this, we come up with a z-score of 0.57. Now what does that mean? Well, it doesn't mean anything until you use a normal distribution table. On a normal distribution table, you can come and you can find the 0.5 on the side, on the left-hand side, and the 0.07. Where they meet is at 0.7157. What that means to you is that there's a 71.57% probability that you will finish this project by the 16th week. Are you worried? You should be. Your boss should be worried, because that also means that you have over a 28% probability of not being finished on time. So pretty scary stuff. But the point that I would like to make is now, rather than giving your boss a swag answer, I'm guilty of that. The boss will come and say, well, what's the likelihood that we're going to be finished with the information for that new class that you're putting online by August? And I'll say, oh, it's 99%. Well, now I don't just have to guess, okay? I can go back and I can calculate that. And I can tell my boss, based on the numbers, I can tell you that there is less than a 72% probability that we will be finished on time. Great stuff.